Okay, let's look at example 13.2. It's a pretty cool problem because we're going to analyze it in two ways. One without drag, and then with drag. So first let's see what happens. How high does this go, delta y, if we launch it straight up at 50 meters per second. We know the mass is 10 kilograms. And we need to probably use the fact that the velocity in the y direction goes to 0 at the top. Okay, well, let's start with our methodology of solving these problems. Would be free body diagram. So while this is in the air, only thing acting on it is gravity in this case, and that's mg pointed down. So we can say that force is a minus mg. When we sum, if we wanted to, we could sum the forces in the y direction and say it's equal to mass times acceleration in the y. And we have a minus mg because it's pointed down. It's equal to the mass times the acceleration in the y direction. This ends up mass times gravity, 10 times 9.81 gives us a negative 98.1. That equals 10. Divide back through by that 10, and the acceleration in the y direction we can verify is the acceleration due to gravity. So you don't have to do this. So let's use the fact that g is 9.81 meters per second squared, and it acts down. Okay, now that we have that, we can say the final velocity squared is equal to the initial velocity squared plus 2 times gravity times delta y, and solve for delta y. V final goes to 0 at the top. We know this was 50. We know gravity, we'll put in a negative 9.81, and we can solve for delta y. I get a delta y of 127 meters. Alright, that was actually just realizing that we had to use the acceleration due to gravity. This was not necessary. This was kind of proving that the acceleration was 9.81. Alright, now let's look at if this was case A, where we had no drag. Let's look at a case where we have drag. Now drag is air resistance, and it is a function of velocity typically. So they give us the force of drag is equal to 0.01 v squared newtons, a function of velocity. Let's do a new free body diagram now because we just introduced a new force. Automatically mg pointed down. Now drag is like friction, it opposes motion, so if this thing has a velocity like this and we're only concerned about going to the top, that would be a velocity vector pointed up the whole time, then drag is going to be pointed down also. So if I sum the forces in the y direction now, equals mass times the acceleration in the y direction, I get a negative 0.01 v squared for the drag going down. I get a minus mass times gravity. We found was if gravity is 9.81 and the mass is 10, we get a 98.1 pointed down. And that's all times the mass, which is 10, times the acceleration in the y direction. Alright, moving the 10 on the other side, I get the acceleration in the y direction equal to a negative 0.001 v squared minus 9.81. Alright, now this is acceleration as a function of velocity. let's use a dz. This is, or it could be dy, I guess, is equal to v dv. Plugging in acceleration, I get negative 0.001 v squared minus 9.81 dz is equal to v dv. Now we need to put dz all by itself, and we end up with v dv over all of this stuff. Negative 0.001 v squared minus 9.81. Now when we integrate from the floor to its maximum height, switch to variables, so delta y is equal to z now. We need to integrate this from its initial velocity to its final velocity at the top, 0. And solving this, you get that z is equal to negative 500 times the natural log of v squared plus 9810. Evaluate that at 50 meters per second from 0 to 50, and you get a delta y, or z, of 114 meters. Alright, if we look at what it was before, with no drag, no air resistance, it made it up 127. So from the ground, one made it to 127. With drag, it only made it to 114 meters. And that's what we would expect.